In knowing how some of the simplest parts inside your database work, you can make enhancements that will boost your application's performance. You already paid 100% for a database. Why stop at just 50% of what it can do for your application? For some cars, at a speed of 95 kilometers per hour, it's cheaper to turn on the air conditioner because an open window creates an aerodynamic drag that requires the engine to work harder. Other cars don't need you to warm up the engine, so you save on gas and latency from your home to the local Starbucks, if you know to start moving the moment the key is turned. It's the same with RavenDB. Once you discover that there are identical ways to perform certain operations that are a lot cheaper, you'll gain optimizations every time these operations are executed. A car can only be optimized in use, but these optimizations can be used both in development and management of your application and its database. Understanding what's under the hood of RavenDB helps you perform simple enhancements that produce significant boosts to performance, reductions in latency, and savings on the cloud. Today, RavenDB CEO Oren Aney opens the hood to what is going on inside his database to show you practical examples on how to use this knowledge to develop faster applications. Feel free to ask questions by clicking the Q&A button at the bottom of your screen, and Oren will be happy to answer them throughout the presentation. Enjoy your presentation, and here's Oren.
Hi, everyone. Thank you for joining me today. I had a hard time deciding at what level I should talk today. On the one hand, I really love talking about the bits and bytes, about how RavenDB is composed, binary trees, how RavenDB achieve the ability to be both transactional and performance, stuff like that. For the most part, however, I don't think this would be relevant for most people. I find this fascinating, and I recently did a presentation that talks about how databases are built from the ground up. But for now, what I want to give you some details that you can immediately utilize in your usage of RavenDB. So let's talk about what we're going to do. I want you to understand what RavenDB is doing. In many cases, people assume that a database is magic. It's just something that happens and somehow it's supposed to make things a lot easier or faster or whatever. And I certainly had that scenario when I started working on RavenDB almost 15 years ago now. And it turns out that a database is also an application, also has the same constraints that you've seen in your system. The major difference in a database is that it tends to have a well-defined scope of work, and that for the most part, there is an expectation that it will just work and everything should move on and all sorts of stuff like that. So let's see what we're doing behind the covers, and that's going to help you to utilize RavenDB to the best possible extent. It's also going to give you some general information if you need to troubleshoot and operate RavenDB in production. So let's talk about what we're doing. RavenDB manages resources, and those resources are typically CPU, RAM, and disk. There is also the network that we have to consider, but for the most part, we don't really care about that much about that. There isn't much special about what RavenDB does over the network. What is RavenDB doing for compute? So we have a CPU, and we use it to index, to process query, do all sorts of background tasks that we need to do, such as ETL, backups, etc. Doesn't seem like there would be much of interest here. For RAM, we use memory map files, and we heavily cache some details in memory. We also do a lot of work around memory management directly in RavenDB. Now, RavenDB is written in C#, which is a managed language, but for the most part, the way that we operate excludes a lot of the traditional idiomatic C# code. For example, memory allocations, which is very prevalent in many .NET code paths, is something that we heavily frown upon. Now, the question here is, why do we frown upon that? Why is memory allocation a problem? And this comes back to managing your resources. If you allocate a lot of memory, the GC is going to intervene and clean things up. But the GC is not free. And if you don't control your allocation, you may spend the majority of your time just cleaning up garbage. It turns out that there are several relatively simple processes that you can use. Pooling of objects is probably the most common one of those, and the .NET framework in the past 5 or 6 years has made tremendous steps to make this easier. We have array pool, memory, and stuff like that. There is also a native memory. And for the most part, RavenDB is going to use native memory as much as possible, so it's not even visible to the garbage collection. And that's, again, the less work the garbage collection has to do, the better we are, because we can spend more compute cycles doing meaningful work. Finally, we need to manage the disk. And there are two aspects here that we really care about. One of them is, how do we make sure that RavenDB is transactional? That once you wrote a transaction, no matter what, that data is going to be safe and persistent. And the other side of that is that we need to manage the I/O operations. The faster we can process the I/O, the better things are. I went to my support team. I have a room, there are all of the support engineers are sitting there, and I asked them, CPU memory or disk, what should I care about? What should I spend money on if I'm caring about performance? And the answer was 100% speed up the disk. But why? Why do we care so much about the disk? And the reason for that is, consider what we are actually doing. RavenDB is a database. It's all about data. The faster the disk, the faster we are able to run. Now, theoretically speaking, you can give me enough memory to run the entire dataset in memory. And RavenDB will absolutely do that given the chance. But for the most part, that is not a good trade-off in terms of price performance. Even NVMe disk, even on the cloud, are significantly cheaper than RAM. As for compute, more CPU cores, faster CPU cores are better. Now, in general, given the choice of more cores to faster cores, go with faster cores. Now, the way that RavenDB works in terms of compute is interesting. Let's look here. RavenDB is managing the compute operations in several meaningful ways. So let me try to explain how it works. The more work you do, the more work you give to the system, the more it needs to manage. So there are two types of work that we care about. One of them is request processing, and the other one is background operations. Background operations such as backups, indexing, stuff like that. In order to create better accountability and to prioritize the data, RavenDB divide the work into separate threads. And we make sure that as long as you have more than 2 cores, at least one core is always excluded for background work. So even if there is the need, background work is filling up all of the CPU utilization, you have at least one core that is available to do other things as well. Now, but let's first talk about the I/O and what it means, and then we can discuss compute and memory. So we can put the entire database in memory. It helps, but it's not that good. The reason for that is that for writes, RavenDB must hit the disk. Why? Why do we have to hit the disk? And the answer is simple. RavenDB is transactional, which means that one of the guarantees that we give you is that RavenDB would be durable. What does it mean to be durable? Durable means that if you pull the plug on the machine, something happened, then RavenDB is going to be guaranteeing that no data has been lost. Now, this actually become quite complex. So let's talk about how RavenDB actually operates. In general, each thread, each database inside of RavenDB, and each index inside of those databases has its own dedicated thread. And those threads are going to be issuing I/O operations. It's important to understand that in the process in which we're writing to the disk is somewhat involved. I will get to that in a bit, but it's important to understand that what is actually generating parallel I/O. The database, as you write to the database, it's going to generate I/O. In parallel to that, all of the indexes are running and may also generate I/O. So if you have a single index and a single database, only 2 threads at a time are going to generate I/O. This is not actually true because we're doing ASIC I/O operations, but it's good enough. Now, when we're talking about I/O, it's a bit more complex because there are 2 types of I/O that we care about in terms of writes. On the one hand, we have I/O to write to the write-ahead log. Sometimes we call it a journal. Whenever you write a transaction, RavenDB needs to make sure that this is persistent. Writing that directly to the data file is supremely expensive, so we don't do that. Instead, what we do, we write the intent to write it to the log, and we need to make sure that that write is durable. The way that we do that is we use those flags, and on Windows, those are POSIX flags, and on Windows, we use file flag no buffering and file flag writer. And the idea with those guys is that they ensure all the way to the hardware that any write that I'm doing is going to have these 2 properties. First, it's going to use DMA, direct memory access. The second, it's going to be sent to the disk with a flag called FUA, force unit access. This is the flag that tells the disk this must reside on the physical hardware. This must survive power loss. So it is significantly more expensive than a typical write. But we have to do that in order to ensure the durability of the data. Now, those are just writes that we're making to the journal. When and how are we writing to the data file? And the answer here is that we're not. We're really not. What we're doing, there are actually 2 steps that you can take along the way to make to actually make writes to the data file. And let me see if I can expand that. First, we need to put the data somewhere. This is called a sketch file. And then we move that to the data file, and then we have to sync it to disk. The whole process is running in a synchronous format in the background. This is what I meant when I said that even though we technically have only I/O for those, there are also additional I/O happening behind the scenes. I will touch on writes in a bit more in a moment. Let's talk about reads. Reads happen in one of 2 options. Not one of 2 options. For documents, for data that resides in the database store, we are always using memory map I/O. And RavenDB has structured the data in such a way that we don't really need to think about the data. We can immediately write and operate on that. What this means is that in many cases, RavenDB is just going to be able to answer your query by jumping to the right location in memory and flushing the data directly to the network. For indexes, the situation is somewhat more complex. We also memory map the data in the indexes, but there we use Lucene, and Lucene needs to do some additional operation as in-memory data structures. Regardless, most of the data is meant to reside as memory map, and most of the read operations that we do in RavenDB are done through a memory map IO, which means page faults. Now, the more RAM you give us, the better we are, because the more values can we cache in memory, the less actual page fault you're going to have. However, something that's really important, in general, latency is so much more important than throughput. So if you have, if you look at the raw numbers, a hard disk and an SSD have roughly the same throughput numbers, maybe 100 megabyte per second here or there. But if you look at the latency, so let's say that I can write to a hard disk at a rate of 500 megabyte per second, and I can write to SSD at a rate of 600 or 700 megabyte per second. Doesn't really matter that much for our purposes. It matters more that a single write to, or single read, which is typically more expensive in these cases, from the disk can take dozens of milliseconds on a hard disk and microseconds on an NVMe disk. And that means that, again, I can choose to have better disk, which is somewhat more expensive, but with a lot less RAM, which is much more expensive. Another thing to notice here, almost all of the expensive writes in RavenDB are here when we are writing to the write-ahead log. And the reason this matters, it matters because it matters because those are always sequential writes. So we're never actually running in doing random writes or stuff like that on the write-ahead log. We allocate the space on disk, we write to it in a sequential fashion, which is the fastest way to go about it. That's it. On the background, which much lower priority, we have this, and this does do random writes, but no one is going to be waiting on this. So that's important because we can take more time doing that. Now, let's talk about how we're actually handling writes. And the process is fairly simple. Whenever you need to write documents or attachment, timestamps, the whole thing, we are writing them to in-memory buffer, which called the scratch files. Once your transaction is completed, we are going to start processing that. And then we are doing a whole bunch of work there to reduce the amount of IO that we have to do. We take the modified buffer, compress them, merge them among different transactions, fold them on itself, do a whole bunch of work, and eventually the value goes into the one. It's really funny, but we had one use case one user who tried to benchmark RavenDB. And the way that he benchmarked RavenDB, he spun out about a dozen bulk insert processes that wrote a small document, name equal Oren or something like that. And what happened was that RavenDB was able to process that very quickly at the rate of tens of thousands or hundreds of thousands of writes per second. And then he was watching what's going on the disk, and he says, hey, you're only writing like 15 megabyte per second. What gives? And the answer was that RavenDB was actually able to optimize this, to take all of the writes from all of those bulk inserts, merge them into a single stream, compress them, and most of them were roughly the same document, so we got a really good compression rate, and then throw only the final data to the write-ahead log. And in the background, we also had writes to the data file, but it wasn't enough to cause the system to slow down or something like that. Now, there is a term called MVCC. MVCC stands for multi-version concurrency control. And the idea here is that at any given point in time, there may be multiple versions of data in place. So let's assume that they have this. Okay, so this is the document that they have in place. Now I'm doing an update and I want to write it like this. It works. However, consider what happened if there is currently a read transaction that may be observing this guy. Oh, 1 second, you're not seeing the console. Okay, Felipe, are you able to see this now? Okay, that's good. Thank you for noticing that. So anyway, we have this document, and now I'm updating this document to a different value. At the same time, so this is the write operation. At the same time, we have this thing, and this thing is a read operation. How is it going to happen? There are going to be conflict between them. We have to take log, stuff like that. In a typical relational database, lock and latch management, lock is on a row level, latch is on a page level, or vice versa. I don't remember at this point. Takes over 40% of the runtime of the system. Absolutely insane. Instead of doing it this way, what RavenDB is doing is very different. We are saying, hey, we're going to use multiple copies. So whenever you modify a value, we are not modifying that in place. So this is on raven.voron, page 19. Scratch 000, page 15. So this is what we have. This is the actual value that we have, and we know that it's on page 19. We modify this and we store that in a Scratch buffer, Scratch file, as the 15 page there. And we have a table that maps between them. The update transaction is going to observe this value. The read transaction is going to observe this value. RavenDB implements snapshot isolation. Only when there are no more observers that may be looking at this page will RavenDB copy the data back to the data file. Now, that's cool. That's actually really cool because the concept is that we don't really care about interactions between reads and writes. The system just happened to work this way, so we ensure snapshot isolation. Now, the problem here is that the Scratch files will get full, and if we have a single value that is updated constantly, we may end up with a lot of copies. Stuff like that. So there is a background process that would copy this value from here to here when we're done. So far, so good. But this is called a flush. Moving from the Scratch to the data file is something that we call a flush. Now, it matters because we are not trying to make this durable. A flush operation is just something that we do to clean up our in-memory data. We don't assume that this is durable. So we need to sync the data. Sync the data means call fsync, or in Windows, flash file buffers, etc. Only then, this is on the Raven data file. 11.1.5, sorry. And this is the data file basically. Only then can we be sure that the data is actually persisted, and then we can clear the logs. Now, there are a bunch of things that we care about here. First of all, flashing from the scratch to the disk is cheap. For the most part, this is basically a mem copy between two memory map location. It should run at memory speeds. Syncing is so much more expensive. So we try to delay that as much as possible. We ensure that only a limited number of concurrent syncs are going to run on any given point in time on a disk. And somewhere I had Chrome open. And you can actually see all of those details in your system. Go here, go to IO stats, give this a second to start up. And here are the details. So this is a journal write. This is this guy. This is a flash. This is copying from the scratch file to the data file. And let's search for a sync. Here is a sync. In this case, very quick, very nice, blah, blah, blah. Now, let's make it harder on RavenDB. Now, remember that this is a cloud instance that has basically 0 resources behind it, both in CPU, memory, and what's the problem? var I, sorry. Okay, so now let's look at what's going on, and you can see that I'm using a lot of CPU. I have only 2 cores, and I'm indexing quite heavily. Nice chunk of memory, and we'll use more over time. Let's run it again. Now I have 2 concurrent write processes that are going to run. Now let's see what's happening here. And I'm putting the system under quite a bit of load. Okay. So now you can see that we're starting. Here is a transaction. Notice we can see that we compress the data, and we spend 100 milliseconds compressing the data. Couldn't really get it to compress that nicely. Oh, no, we got here. Okay, the original size. It doesn't report the output size for some reason. This is the time that it took to actually write it. Oh, you can see this is 2 megabyte. The original was 11 megabyte. Now here we do a flash. Now this is suspicious. I will notice that this took 2 seconds to complete. I will talk about exactly why, and this is again. And now we have the actual sync going on. So remember, I said that the sync is so much more expensive than the flash, but we're not seeing that behavior. Why is that? And this is the reason. The system as it currently stands uses a lot of memory. So what happened is that the underlying system is going to be very aggressively pushing data to disk. When we are flashing, we are doing memcopy. But if the destination or the source that we push was written to disk, we may need to do a page fault. On the other hand, here we're writing fsync, which is expected to be expensive, but we already wrote all of the data to disk. We just need to flash the buffers. So in this particular scenario, we're actually seeing the inverse of what we would expect. Okay. Now, here are a few other things that we have to consider. Given the MVCC nature of RavenDB, what's going to happen if I have a long-running transaction? It's going to block me from writing to the data file. Why is that? Because if you remember, I had page 19 here. And if I have a read transaction looking at this, I cannot modify that. So long-running transactions tend to be extremely rare in RavenDB. The only common scenarios where you run into those are if you stream a lot of data out, if you run a full backup, if you're doing an export, those sort of things. If you combine that with heavy write load, then RavenDB is unable to push the data to the data file, which means that we're going to see more and more scratches. We're going to see more and more log files because we can't push the data to the data file and then sync and then delete the log files. In general, this is a good thing because we are trading off the load on the system with disk utilization, basically. Over time, the more work that we do, the more over time the retransaction would complete. RavenDB would then push all of the changes back to the data file and discard all of the log file and scratch files that are no longer in use. One thing to note about this scenario, what happens if we need to run recovery, if we reboot the system midway through something like that? RavenDB would then have to scan through all of the log files that exist on the disk that haven't been persisted yet. And then it would need to run through all of those. Why do we care? Why does it matter? It would need to run through all of those to ensure that all of the writes that we wrote to the write ahead log have properly written to the data file. And if we are running on low IO machine and in the cloud, this is very common. This may mean that you're seeing the restart of RavenDB may cause us to load and access randomly to the data file on a huge spike of IO. And sometimes you run through your IO credits and you're limited to very small number of IO operations per second, and that can slow down your RavenDB startup time. For the most part, it doesn't really matter that much. You tend to have one or two log files in most operation. It doesn't need to scan too many details, but a restart after a huge import or something like that may cause you to have a lot of data. You can also look at this in here in the storage report. Let's look here. You can see that I have 2 GB of data file and almost a quarter of that in temporary files. And here are the scratch files that I'm using. So that's where all of the temporary data resides until we are able to actually write it to disk. And this is the actual IO behavior that we see. Hopefully we see that in a second. There we go. Yeah. Notice that we also have here in the timeline view, you can see that there are parallel operations for each index. Now, this is actually something that is quite important because RavenDB is going to attempt to limit the number of concurrent flash operations on a per drive basis. So sometimes we see users that put all of their data on a single disk, some that are spreading indexes and data files on separate drives. and that can allow us to parallelize the overall I/O on the system. We have a question from Felipe. When we're running on a cluster environment, the sync to the other node, it's done after the commits are confirmed to the local disk. Yes and no. Let's talk about why yes and why not. The way that it works, RavenDB force commits to the local disk and then immediately start pushing to the other nodes. Now, what do I mean commit to the other disk? I'm talking about writing that to the log file. This ensures that no matter what, we're always going to be the write has been made durable. If we crash right now, we're going to start running and we're never going to lose any data. However, we force write to the local disk and only then send the data out. Otherwise, we risk, if this is asynchronous replication mode. Otherwise, we risk the options of another node is down and we cannot commit our own transaction. Now, you can also do this when you write. And what this says is that I want you to return here only after you committed to the local disk and another disk in addition to that. So that's quite important because that means that at least two nodes in the cluster have this right. For the most part, this is something that I would consider to be relatively rare to want to do on a proactive basis. Now, let's talk about reads in RavenDB. So in most cases, you have a lot more reads than writes. This is not true in all cases. For time series, for example, this might not be true. But for documents, you're almost certainly going to be reading a lot more often than writing, which means that RavenDB is going to spend time preparing for that. What do I mean by this? So the data is memory mapped. And that means that we don't need to manage buffers. We let the operating system handle that. But it also means that we can access any given data point by just using pointer arithmetic, which means that the data structures that RavenDB uses internally are zero copy. They're not. So one way of doing that would be to say, store it like this. I'm just storing that as a JSON or maybe compressed JSON or something like that. But I'm not actually doing that. What I'm doing, I'm storing that and it would look something like this. Imagine that I'm storing it as the raw dictionary. Why am I doing that? Because this allows me O1 access to the data. So I don't need to do parsing. I don't need to read the data from the on-disk format to the in-memory format or something like that. And that has a huge impact on what's going on. When you read a document, what happens here? What happens here is that this is the document that I have stored. I'm looking up this document. I'm finding the actual position in memory, jump into that, and then output the JSON directly from that value. So I'm basically just give me the pointer, write a JSON to the network, and then I'm done. And here we go. So it also means that projection from large documents are really cheap. If I'm going to look here and so I have a relatively nice document and I want to do something like this, give me just the product IDs. This is cheap to do. I don't need to parse or the entire document in order to do that. I can just jump directly to those values and pull the data out immediately. It also means that, again, because of MVCC, reads never block writes and vice versa. Queries are really cheap. So let's go here and look at the number of data. I have 1 million records here. So I'm going to run this, and queries are really cheap, except that in this case, this is not cheap. This is taking time, and it takes between 15 and 17 seconds to complete this really simple query. That kind of sucks. Okay, I'm very precise in this case. And you can see that this is being quite active. Now, if I'm searching for Paris, I'm getting the result almost instantly. For London, quite quickly. What's going on? So this is a key aspect of RavenDB. Queries are always cheap, but we just saw that they aren't. So queries are cheap because they're using an index. If there isn't an index, RavenDB is not going to go and do a table scan. Instead, it's going to build an index for you. In fact, this is exactly what's going on right now. And you can see that we're doing that right here. In a couple of minutes, we're going to be done, but not at this point. We are also still writing. We have a whole bunch of other indexes that are running, and this is a pretty small machine. So the fact that indexes are created on the fly has a major impact on the overall behavior. RavenDB manage all of that for you. You don't need to think about that, but it does mean that you can, that RavenDB assumes that most queries are going to repeat itself. And if you change your behavior, you're going to keep using that scenario. A good story here is that if you update your system, update your version of your software, and it change the queries that you generate, RavenDB will automatically adjust. That's the good side of that. The bad side of that is that if you run in once in a blue moon query, RavenDB would still need to create an index for that. That's not so nice. Another thing to remember that RavenDB by default does buffer reads. What is a buffer reads? Let's look at this. Await session query. So what is this? What is this guy? This is give me all the users. And RavenDB internally would get all of the users, load them into a single buffer in memory, and then send them all to you in one shot. Why? Because if you are working with small set of values, and RavenDB by default would try to use small set of values, we're going to be able to give you the data much more efficiently this way. However, let's try to kill this system. And in this case, you can see that there are 2,000 results here. And let's remove the page size, so it will give me everything. So RavenDB prepares the data, and then it sends all of that out. There is a total of 16,000 results in this case, and we get that. But the idea here is that RavenDB had to keep all of the results set here in memory, and then pushed it down. Now, this sounds like a really, really, really bad idea. Why? We have to keep all of these resources in memory. What happens if this is tens of megabytes, hundreds of megabytes? Well, the answer is that yes and no. What do you mean by that? We have to keep it in memory, but remember how RavenDB works. What we actually keep in memory is the document pointer, which point to memory application. So even if I have 100,000 items here, the size that we take is not 100,000 times, I don't know, 8 kilobyte for average document. This is 100K time pointers plus some metadata. Far, far less memory. So it's much better for our usage. It still sucks because RavenDB have to prepare the entire thing before we send it to you. And what is worse from your perspective on the client side, this is now on your side of things, you have to create a list of 100,000 items. And this is now probably in managed memory and you have to deal with that. Notice that in cases like that, RavenDB will give you an alert. Hey, there is an issue. This is probably not something that you want to do. It's going to slow you down. Now, RavenDB has a feature called streaming. And this allows you to stream through the result, and RavenDB on the server side would push you the data. And it would immediately show up on the network and you process that, etc. Now, one caveat about using streaming. So the typical way to handle that is something like this. You're doing something like this. Now, if this takes a while, it may be possible that RavenDB is now sending the results, and you're now processing at a lower rate. If the divergence between the rate that RavenDB processes the result, sends the result, and you process the result is big enough, you may end up timing out on the request because RavenDB sent enough data and you didn't process that quickly enough that eventually RavenDB says, hey, no one is on the other side to pick up the phone and continue that. Eliran, can you give me some details about this that we can talk in this forum? The answer here in general when using streaming is that you typically want to do as little as possible in the streaming. You typically write it somewhere, or if you're doing some processing, make sure that you do in-memory processing and not call to somewhere else. Something that is likely going to cause failure is something like make remote call per item. And that is almost certainly going to cause failure if you have a lot of data. Why? Because let's say you're spending 100 milliseconds processing each item, but RavenDB is sending you the data as quickly as it's possible, and there is a traffic jam going on here. If you want to do stuff like that, subscriptions is the preferred options to handle that. Okay, so let's talk about reading and from the client perspective. RavenDB has a cache by default. The typical, the general idea is that if you run the same query twice, In most cases, remember, reads are much more common than writes. Most cases, we can skip actually processing the query. So from users, something like this. You run it one time and RavenDB sends it to you. The second time that you run it, RavenDB is going to remember that and use those results. We can actually see this here. Now here again. Oh, sorry, it is still indexing. Let me shut down this so you'll be able to see this properly. So now we are done. Run the query, take 42 milliseconds. Run the query again, and let's see how that looks like. So run the query. And you can see something really interesting. You can see this is the status code, 304. And I can disable the cache. And this is actually funny. You can see that with the cache, it's slower. Why is that? Because the value that we got includes the timing. Somewhere around here, there is the server timing. Here we go, duration millisecond. This is part of the cached request. And the reason this is important is that repeated queries are actually going to go into the same, repeated query are going to go into the generate the same query. They're going to be cached at the client side. When we send them, we're going to send the e-tag of the query, and this is going to then return 3 or 4 from RavenDB. And RavenDB actually has a dedicated code path to answer, hey, nothing changed, as quickly as possible. We have Michael or Michal who is asking, for how long RavenDB can cache query? How does it look like for multiple concurrent scenario querying different documents? And the scope for the cache is the document store. And you can actually see here in the request executor, the request executor has a cache, and all of this is kept here. By default, we keep around the last 2,000 requests, 2,000 unique requests. We're not experimenting based on time, and concurrent users that issue the same query are going to give you the same result. Now, there are actually 2 modes for caching here. One mode in which we'll just remember that we have the results and tell the query, hey, did anything change? And another mode, which we call aggressive caching, which you can enable like this. And inside this scope, queries that exist in the cache will not even hit the server. We can answer them directly from the cache. We have Eliran. I had the exact same issue described here. He's talking about the streaming and the processing. We're trying to read from the stream, manipulate the document, took some time, and then wrote it back to the DB. Sometimes the stream would disconnect. You ended up telling me about it in the support ticket. Well, yeah, I'm pretty sure this is why I put that in the presentation. Something that is important, you can see in many cases, people are going to issue queries such as stuff like this. Now, if you do something like this, it's going to kill the cache. Why? Because each invocation is going to generate a different value. In most cases, move it to minute granularity, 5-second granularity, something like that. It's going to give you much better results because you're actually going to be able to cache that. Now, here is a good example of that. So just this is on an hour boundary. Select your need based on what you actually want to do. Here, a bunch of expensive queries in on a big array between start and end, where this covers a huge range of unique values, negation queries. So something like this is expensive. In general, what we want to do is don't do those sort of negation query. Or try to do it the other way around. The reason for that is that the way that RavenDB actually manage the query, we talk about in a second. In some cases, you may have code paths that query over range that has a lot of unique values. That's painful for RavenDB to do because we have to go over each one of the unique options. If you can do that on numeric values, this is much faster. And as of RavenDB 5.0, datem queries, range queries on datums are automatically optimized for you. So this is the issue. RavenDB internally implement queries as, or to be rather more exact, Lucene, which is what we use, implement queries as set intersection. So bound false and born at between this and this says basically intersect these two. Now, this may be a problem. Consider that born@, may have 100,000 unique values, which means that in order to do this intersection, we have to find all 100,000 items that are in this range. It would be much better to issue it like this. Why? Because this is now going to run as a numeric range query, or even as this. Why? Because this is because now we know that the values are the set of values are small enough that we can apply different optimizations. So the scope, I don't want to go too deeply into this, but just understand that this query expresses the same thing, but how they actually work is quite different. Another thing to take into account is sorting. RavenDB lets you do sorting any which way you want, but this is an issue. We have to do the actual sorting. Sorting has a cost of n log n, where n is the total number of results. So take a look at these two queries. They're probably going to have the same results, but they're going to have drastically different performance cost inside of RavenDB. Why? Here is take 100 million users, sort them, and give me the last 10. In this case, take only the active users and give me the last 10. And that can have a huge impact on performance, as you can imagine. This is not for immediate operation, but just something you would know. We are currently working on something we call Corks. This is a long-standing background process that we have to replace Lucene. The current plan is that we can get to it by the end of the year. And we found that Lucene is severely limiting what we can do, but on the other hand, it also extremely rich. So replacing that ended up being more complex than what we expected. Let's talk about computations and how they work inside of RavenDB. So RavenDB, most of the computation is on request processes, indexes, stuff like that. Now, they're shown here in the priority that we run them. So how do we manage that? And we utilize thread priorities at the OS level to manage that. So consider this scenario. The first priority that we have is to process requests, maintain the cluster, those sort of things. We are generating, we are using dedicated threads, which are long running, name and prioritize appropriately to scope work. This ensures that we are running on the relevant, we are able, let me just, this ensures that we are able to give the proper priorities to different operations. Consider that in this case, I have one operation that writes quite a lot to the database. I have quite a lot of indexes that are running. At the same time, I need to process requests, and the system in some cases may hit 100% CPU. I need that to be accountable at all times. So I can go here and see, that might take a while on the load, but you can see exactly what's taking the processing time. This is the transaction merger. This is the thread that actually writes to the database. This is what runs the patch operation. This is indexing of a particular index. You can see exactly where the CPU processing goes. Those things tend to be for a request processing. Unmanaged threads, this is typically the GC. And you can see that all of the others, you can typically say what's going on. And this is very important for the accountability, so we know what's going on. You can also go here. Remember, this is a live server. It's currently doing work. It's currently in operation. What I'm going to be able to do eventually is to tell you exactly where the CPU goes. So not here. Okay, so we can see here. Let's go down and try to see where the CPU goes. So a lot of the CPU goes here. Some CPU is spent mostly here. So in indexing threads, I can run it again and might be able to capture something more interesting. But the design is meant to ensure that we will always have the scope that we need. We're always going to be able to tell you, okay, processing index is not going to overwhelm the system, even if we have dozens of indexes on just 2 cores. We are always still going to be able to process a request. You're always going to know what's going on and things of this nature. For memory, I mentioned the managed versus unmanaged memory. And let's look here. You can go, and again, running system, underload, and you can see the details about exactly what's going on. Right now, we are doing heavy indexes, so we have about 0.5 gigabyte of managed allocation and 100 megabyte of unmanaged allocations. We can put it down to specific threads and what they're doing, so you can tell exactly what's going on. You can do something like this, and this would force a GC and give you all sorts of interesting details about exactly what's going on. There is also this. And again, remember, we're running on a live system, heavy load on the system, and this is typically 5 to 15 milliseconds, 5 to 15 seconds to run. And now you can see exactly what's taking, what are the allocations that are happening on the system. In some cases, this can be really important to understand exactly what's going on. Most of the memory that RavenDB uses on a normal system is done through unmanaged memory. The one caveat for that is that Lucene is using quite a lot of managed memory, part of the reason that we want to replace that. All of the design in here is meant to reduce GC pressure and GC costs. We're using, pooling, doing a whole bunch of things in order to reduce the amount of time that we spent in memory management versus the time that we spent in actually doing meaningful work. This is interesting. You can see that this system is operating with very little available memory. So you can go here to the system and ask it what's going on. And this is the total memory that we have. There is 70 megabyte that is free, but there are 700 megabyte that are available. And this is worth noting what's the difference between free and available. So free means that this is the amount of memory that the host isn't currently using, and but there are 700 megabytes that are available. Remember that RavenDB is using memory map files. So when we looked at the data, all of this space is being used by memory map files that the system can discard without cost, because it's able to reload the data from the disk. So when the whole point of your memory is to be used, RavenDB will use as much of it as possible. So unless you actually see this value being high, the actual memory used by RavenDB, don't worry about it. And even in this case, you can see that let's run it again, slightly roughly the same numbers. And for the most part, I'm looking at this, the working sets, how much I have, those sort of things. And Iran is asking, is it recommended to remove all indexes once in a while, or does it ignore old ones by default? For example, changing how you query the code can leave automatic indexes unused after the change. This is a great question. Let's go and try to understand what we're actually doing here. So I'm going to go here and look at this. So when you look into your indexes, you can see there are a couple of types. This index is idle. What does it mean that an index is idle? It means that no one queried that for long enough that really says, hey, I don't need to pay any attention to that. This is only going to run when there is absolutely nothing else for the system to do. Just to give you some idea, let me see if I can find it. No. Index state. Here we go. So index demo to idle, we don't care about all those. So notice that this is something that happens automatically. RavenDB notices that RavenDB notices that no one is using that, and then it just kills the index. And yeah. Talk about this, and somewhere around here, there's the actual impact of this. Let me see where it's at. So set state, and somewhere around here, I can't remember, we are deciding what do we do on idle. And what we do typically on idle is we only run it where there is nothing else for us to do. Now we are about running out of time, so let me see what else I want to cover. But to answer, Eliran, just to answer your questions, for the most part, RavenDB would manage that. There isn't a huge cost to that. It's just going to spend CPU cycles that you otherwise would be not using. In some cases, this is really good because you may have a query or that you run once every week. So RavenDB would only maintain that for in the background, and you run the query, you get the result, and you move on. So typically, RavenDB, people think about RavenDB as just a store for documents, and then they try to store data into it that you don't necessarily need to do. I recently had a user where they wanted to store a JSON string in the document itself. So I have something here. And this is not really useful. So there are two things here that you need to understand. First of all, RavenDB would compress large text fields like this. And in many cases, that can dramatically reduce the cost of the index. But given that if you have a large string, you tend not to actually want to do something with it, you can just add it as an attachment. And then you can just add something like that and not really think about this. And this would just be an attachment. You can access that, you can open it, and normally you don't really need to think about it. Same thing if you need to store binary data. I had a user who stored a base 64 certificates inside of RavenDB. I mean, it works, but that means that you had text fields that were 10 or so kilobyte in size. And you can store that as attachment, that would be just 7 kilobytes because of the difference between base 64 and binary encoding. RavenDB also has the notion of counters. If you have some values that are constantly changing, you can use them as counters here and not really have to worry about locking of values and things like that. Matthias is asking, is there a limit on attachments? Is it a good idea to store gigabyte of video files as attachments? There is no limit for attachments. You can store multiple gigabyte values inside of RavenDB. The question that I have for you is, what is it that you're doing with that? If you want to store data that is relevant to the document, go ahead. If you want to store RavenDB as the video backend for YouTube, don't do that. Because again, the typical scenario for RavenDB is that the data matters. If you just need to store the raw data for storage, retrieval, something like that, you may want to use something like S3 or something like that and just store the value inside of RavenDB, the URL inside of RavenDB. A lot of that depend on what is the meaning of the data. So you have to answer that. A good example is that you may store video inside of RavenDB of an MRI scan. That absolutely should be in there because it's tied closely to what you're doing and all sorts of stuff like that. On the other hand, if you want to stream videos directly from RavenDB, probably use a dedicated system for that. Okay, so I mentioned the counters, and finally I had a user who came to me and says, hey, I need to store 10 billion items inside of RavenDB. Can I do that? The answer is, yeah, sure, you can do that. What are you trying to do? And he was trying to store values that come from sensors. And if you want to do stuff like that, a better solution for that would be to utilize maybe employees, utilize the time series values that allows you to track values over time. They've been tested to billions of items, and they are storing the value in a much more compact and much more compact form. Another thing that I want to talk to you about, let's kill this. Let's take a look here and see what takes up all of this space. You can see that we have 2.7 gigabyte of this space for orders. Makes sense, we have quite a lot of them here. I'm going to go here and enable compression on the orders collection. And now I'm going to go here and compact the database. This is going to take a while. I'm going to let it run while I'm speaking. What it needs to do, it needs to read through all of those, rebuild everything. It's going at a nice rate if you look at that. But it's going to take, for millions, it's going to take some time. I will explain why this matters in a bit. So let's talk about concurrency. We have the question from Eliton. I'm hoping that I'm doing justice to the way that you pronounce the name. I'm assuming that I'm not. How to work with concurrency on the application side. So by default, if you do absolutely nothing, here we go. So in here, I'm going to modify two threads that we run it. What's going to happen? One of them, both of them are going to know that they were successful. Both of them will manage to commit the value, but one of them is going to overwrite over the other. So in this mode, we have last write wins. We can say this. In this case, one of them would lose and get a concurrency exception. So far, so good. But what happened in a cluster? Let's go here, talk about it. Right now, in this case, I have just a single node. But if I have multiple nodes going on, we have to consider what sort of system we have. By default, RavenDB is going to write to a single node in the cluster. You can change that. You can go here. And specify, go here and specify write to different nodes, or almost write to different nodes based on some session content that you use, stuff like that. But for the most part, you're only going to write to a single node at a time. So that's going to be helpful for concurrency exception. That's not 100% guaranteed. If you have two clients, one of them is hitting RavenDB, one RavenDB node, and the other one had fell over to another node, you may end up with a conflicted write. In this case, RavenDB is going to select one of them as the winning write and overwrite one another. There are features that we have that controls that. You can specify here what is the conflict resolution that you want. And that will allow you to control exactly how to do that. That allows you to control even to run your own code that decides how to handle it, etc. You can also use cluster-wide transactions. And cluster-wide transactions are enabled using this mode. In this case, RavenDB will guarantee that one of them would fail and one of them would be successful at the cluster level. So regardless if there is some failure midway, stuff like that, it's going to work. However, this requires you to contact the majority of the nodes. In some cases, this is absolutely what you want. In some cases, this is not something that you want. I like to consider that the distinction between whenever you're registering that I purchase a lottery ticket, what I most care about is to record this fact. And in this case, I would use the single node transaction. If I want to record who won the lottery, then I would use the cluster-wide transaction mode. And we have a question from Ali. Using a time series database like InfluxDB for web crawling, where you need a time series for chat compared to Mongo or Cassandra with a time field, which one would be the correct choice? Using RavenDB time series, that's the answer that you're going to get from me. More to the point, I'm not sure what you mean by web crawling. Can you give me some context for that? The typical time series value that you would store within RavenDB is some value over time over something. So what are you actually managing here? It's important to note that for RavenDB, you would typically tag each individual value and can store additional details about that for later consumption. So product price from digital markets. Let's see. Are you done? Not yet. So let's go. Great. Well, this is something like this is putting a huge amount of load on the database. It has to compute and recompress everything. Unfortunately, it means that I took down this instance. We'll not try to do that. Basically, Ali, prices over time, this is absolutely something you can use directly inside of RavenDB. Let's see if I can maybe make it happen. If not, I will run my own version. Okay, we take a second to run. So you absolutely can do that. It's actually, we have that as a baseline. Oh, come on. Sorry, I'm updating this when I'm running, so you're seeing lots of interesting details. We actually, if you look at the sample data that we run, you will be able to see that we actually show you exactly that, how you can look at data over time. Oh, this is anon, this is, and test sample data. Here are companies, and now you can see here prices over time for certain thing. Now, this is actually one of those cases where we're going to get really good results from RavenDB because we're able to store that value, and you can see you may have multiple sources for this value, things like that, extremely efficiently, and you can do things like this. So show me the results, process that, and all sorts of stuff like that. Okay. Yeah, we killed the instance. So with that, this is a bad instance to experiment on. Okay, so I had a few more questions that we had in advance. How many entries can a single collection? Is there a best practice for stats on very large collections. So this is for Martin. And Martin, in general, there isn't a hard limit. We tested RavenDB with collection that exceeded the 10 billion range. There is a limitation that we have to deal with here, however. And that limitation is that an index inside of RavenDB can have up to 2 billion items. This is a limitation from Lucene. Now, in most cases, this isn't that big a deal because even if you have large collections, you can generally create a shard the index typically based on time or something like that, but this is something to be aware of. It's also, in most cases, if you have very large collection, what you tend to do is you tend to aggregate and do MapReduce operation, and then the limit isn't on 2 billion inputs, but 2 billion outputs of the MapReduce. Sina is asking, can you show the difference between repository and query? The answer is that I put it in hoping that Sina would be here because I did not understand the question. I would strongly recommend against the repository pattern. There is the query object model, and I would also recommend against that. The reason for that is that the API that you get from RavenDB is already very rich. Trying to work with that and hide that is going to be a losing proposition. I wouldn't recommend doing that. We have, now is time for questions. We have another one from Michal. What would you expect from RavenDB infrastructure change for pure performance, single node, 12 cores, 32 gigabyte, to cluster where same amount of total resources, 3 cores times 4 cores, blah, blah, blah. So RavenDB would typically manage that on the write on a single node. Should I expect performance regression by 3? No. And the question is, let's start from the simple scenario. What is it that you're trying to do? If you're trying to write, if you're trying to move from a single node with the potential for failure to a cluster where you have a failure between the nodes, then I would absolutely recommend doing that, if only because that reduces the severity of my support calls. In terms of performance, what is your application doing? Assuming that we just do this, we have a 3 nodes cluster, it's switched over to all of the nodes are existing with one another, but it's all the nodes are replicas of one another. So we have tripled the amount of work the system has to do. Absolutely. The question here is whatever the amount of work that you do is the same. For example, only one of those nodes would run the backup. So that would free the other nodes to do other things without interference. Are you running at 100% capacity? That's also something that you have to take into account. What you can do in general is to go here and specify, oh, I want to balance the reads across all of them. I can also balance reads and writes if I'm providing the context for those operations. So this is not something that I can easily answer. All else being equal, I would say maybe. You actually, the amount of work that you actually give the system is actually higher at the cluster scenario. Because now, in addition to processing off the load, you also have to process the cluster replication, stuff like that. On the other hand, stuff that would cause you to background operations can be isolated to a particular node. So a backup that may hold up the the flash into disk, which may take a long time, would only limited to a single node. So sorry, I know this is not a nice question to give, but it depends on exactly what you're doing. Okay, so thanks. If you have any more questions, now is the time to ask them. I would remind you that if you want, you can go to RavenDB.net live demo. Give me some details about your scenario, and we'd be very happy to provide you with someone, one of our advocates would go over the phone with you and show you some of the nicer features that RavenDB has that suit your scenario. We also have the cloud. You can get a free instance and get started using RavenDB. And that's it. Thank you very much. I hope that it was interesting and instructional, and have a great day. Bye-bye.